So next up we have Jack Simpson. Jack is a computational biologist by training, but now mostly works with energy markets. Last year he gave a pretty much sellout speech about linear programming. And this year he's going to teach us about how we build an electricity market model from scratch. So very pleased to have you. Take it away, Jack.
Thank you. Hi, everyone. So yeah, I'm Jack. I guess for a bit of background on myself, I'm a director at Endgame Analytics and Cartesian Software, where I work with around 30 mathematicians, software developers, and data scientists. I guess as mentioned, I have a bit of a quirky background. So I have a PhD in computational biology, where I was using computer vision and machine learning to track honeybee behavior. But for the last 8 years, I've been gone pretty deep down the rabbit hole of energy market modeling and mathematical optimization. And that's the world I'd really like to introduce you to today. So to set out this talk, I'm really going to try and cover 3 areas. I'm going to give you a bit of background on electricity markets so this all makes sense. Then I'm going to give you some a quick summary of what optimization is. And then I'm going to walk you through developing an electricity market model. So, background. Let's set the scene. We are just at the very start of the energy transition. Over the next 2 decades, the grid is set to undertake an immense transition as coal progressively retires. As you can see from this graph, over the next 20 years, there's going to be retirements of power station, but also a huge build of renewables and storage technologies to replace them. This is the challenge that we are using mathematical optimization to understand and prepare for. But stepping back, what are we retiring the stations from, or what are we building them in? Well, what it is the thing that is actually powering the very lights in this room as we speak, the national electricity market. The NEM connects the 5 eastern states into a single network and is run by the Australian Energy Market Operator. So there's power stations all the way up in far north Queensland, all the way down to Tasmania and South Australia that are all being dispatched and run and dancing together in a symphony. And when I say dispatch, what I mean is every 5 minutes, the amount of electricity that is generated and the amount of electricity that is required have to be constantly balanced. Dispatch volumes and prices are set every 5 minutes and are actually the outcome of a neural network machine learning model that predicts what we have to hit for the next 5 minutes. Each state will then receive a single price that every single power station is paid based off of how much they were dispatched for. And this whole dispatch process is done via mathematical optimization. So to make this a little bit more tangible, what I've gone and done is I've taken a little bit of data on Victoria for that occurred recently, and I thought I'd just walk you through what demand and generation looks like. So, last Monday, this is what electricity demand in Victoria looks like. You can see how you get the morning peak and then the lull in the middle of the day as rooftop solar is really chomping down on demand, and then you have an evening peak again. This trend looks like this. That's what the whole of last week from Monday through to Sunday looked like. And this is the availability of all the wind farms and all the solar farms in Victoria over that same period of time. And just to keep complicating this graph, this is what prices were doing over that period of time. I'll point out 2 fun things. Firstly, prices can go negative, as you can see highlighted at the bottom. So in that circumstance, generators have to pay people to use their electricity. And you can also see that there was an interesting price spike that occurred on Tuesday when it looks like there was a bit of a wind lull as well. So effectively, now that I've set the scene, the goal for today is to use some of this data to build a mathematical optimization to show how these power stations are dispatched and how we actually do modeling to plan things in the grid. We're going to do 4 broad things, which I've kind of summarized here, which I won't go into, so I can hopefully spend a little bit more time in the code. But hopefully this ends up being interesting. But I guess the first thing I will do is I will start by giving a little bit of background on optimization, which is effectively the methodology we use for this type of modeling. So when optimization gets used to describe so many things, but for us, it describes a very specific thing, mathematical optimization, otherwise known as linear programming or mixed integer programming. And it's effectively a form of prescriptive analytics. So if you kind of go up, I guess not quite a hierarchy, but you might have descriptive analytics around what has happened historically. You have diagnostic analytics trying to understand why something happened. You have predictive analytics, which is often machine learning, what will happen. And then you have prescriptive analytics. What should I do? I have hundreds of power stations submitting thousands of bids. I have tens of thousands of constraints. What is the mathematically cheapest way I could dispatch the grid without violating any of my constraints? Funnily enough, ML and optimization play very nicely together. In fact, we use predictions for demand, renewable availability as outputs of machine learning models as inputs for mathematical optimizations. Sadly, optimization isn't as sexy as AI, but what you will see is that you kind of scratch the surface of any industry, and it is kind of quietly doing its thing under the hood. And to give you a bit of a flavor of the kinds of things we use optimization for in the energy industry, we do a lot of future grid simulation. Because if you think about it, there is no historic data set of what the grid is going to look like in 20 years for us to train machine learning models on. We use it to stress test costs, assess the risk of events occurring, and also, as I previously mentioned, the market operator actually uses a mathematical optimization to dispatch the grid every 5 minutes. And this is how it works, broadly, and this is what I will break down in the example when we actually build our model. Really, you've got kind of 4 key components to a mathematical optimization. You have the data set and any assumptions that you are bringing to the model. How much does it cost to build a wind farm? How much does it cost to run a gas peaker? You have an objective function. This is the thing you're trying to minimize or maximize. Usually, if you're doing grid modeling, you're trying to minimize cost. If you work for someone who's investing in a battery, you're trying to maximize profit. You have decision variables. These represent every single granular decision you want the model to help you decide on. So that could be, how much should I dispatch this bid from this power station for this specific time point? One of the nice things about mathematical optimizations is they can be rich sources of data in and of themselves. You can extract, you can run millions or tens of millions of decision variables and see the optimal value that comes out for each of them. And finally, you have constraints. These are the rules that the model isn't allowed to violate. You cannot dispatch a power station for more than it is capable of generating, for instance. So now we're going to use this in a more tangible context. So what I'm going to do is I'm going to simplify it down to just 2 enormous power stations that have a rating, which is kind of their max generation level, and a cost to run. And I'm going to pick the first demand value that we saw from last week in Victoria, and we're going to build an optimization to dispatch these power stations for the cheapest to meet this demand. And so what we'll do now is we'll step through that list of 4 things that are involved in a mathematical optimization. First, we have our data sets and assumptions. What is our demand? how much does it cost to run these power stations? And finally, how much are we actually able to dispatch them up to? Secondly, we have our decision variables. These are for each of the generators, how much is it optimal to actually to run them up to? You'll notice a few little things in this code here. There's LB, which is a lower bound. It doesn't necessarily have to be a positive number. In fact, if you occasionally forget to do this, the optimization will run your gas generator for negative as much as it can, because that will be the cheapest thing to do. Then we have our objective function, which is effectively what we're trying to minimize the cost to dispatch these power stations in the grid. And so you can see we are multiplying the cost of each power station by how much the decision variable of how much to dispatch it. And finally, we have our constraints. And we have 3 constraints in this model. The first two describe the upper limits for how much we can dispatch the power stations for. And the final one, and actually, to step back, you'll also probably notice that these constraints are in the form of a less than or equal to, whereas the final constraint is an equality constraint. However much we dispatch coal and these power stations for, they have to equal the demand of the grid. We run our model, and I mean, you could probably all figure it out in your head what this was going to do. But as you can imagine, once you have millions of, or tens of millions of decision variables running every half hour for decades with tens of thousands of constraints, that becomes a bit hard to work out in your head. So we've got a model. What happens if we now choose a different demand level, like the peak demand we saw in Victoria for last week? We're going to keep the same power stations. The only thing we're going to substitute is that demand level. And it is infeasible because, as you can probably see, we could not actually satisfy demand. We didn't have enough generation capacity available. So the way around this is we kind of slack off a bit. What you do is you still want the models to solve. You just want to know what is the optimal thing to do if there are blackouts that are going to occur anyway. So in this case, we introduce 2 new decision variables. Use, which stands for unserved energy, effectively a blackout variable, and a dump variable, which is just a way to remove energy if there's excess, which isn't really relevant for this example. But the key thing you'll probably notice is I have made the cost of a blackout $40,000. It is very expensive. The model will not want to use this unless it has to. But because there is no actual upper limit constraining how much unserved energy can be in the grid, by introducing these variables into it, I can now get an answer, and it will tell me how much to dispatch my power stations for and how much unserved energy. I have made this model feasible. What else can we do with this? Well, can the model build our power stations if we don't have enough? We can. So in this case, we're going to assume that we're just going to let the model build the optimal amount of a power station. And by doing this, we're keeping all of the previous decision variables, but I've introduced a new one called gas build. And what that is, and it has a cost associated with it. And so now, in the constraint, instead of saying that the amount I can dispatch this power station for has to be less than or equal to a fixed number, I am setting it as being less than or equal to another decision variable, and I'm introducing that into my objective function so that it knows that there is a cost for building and dispatching this. What about renewables? Well, in the case of renewables, they're quite similar to our other power stations. There's just one additional complication. It's not enough to just have the rating of the power station. They are also limited by what the weather is doing at any point in time. So in the case of this example, now that we have an enormous solar farm and a wind farm, we have assumed in this example that their proportional availability is 0.6 and 0.7, and we introduce that into their availability constraint here. And once you do that, it works just the same as everything else. There's a lot more we can do with this to build on top of this foundation. You can now start layering multiple times into this optimization. I'm not going to go into that because the amount of data and the code gets quite verbose. But as you can imagine, instead of just having a power station, a single decision variable representing a power station, you can have a decision variable representing a power station and an interval of time. You can also have different levels of demand for different states, and you can have different power stations located in them. You can have constraint equations that represent transmission lines or interconnector flows. There's also additional things we can put in that represent more of, I guess, the richness and complexity of the system. There are minimum generation requirements associated with certain types of power station. For instance, a lot of coal units have to either be off, or if they are on, they are generating a set minimum amount, and it takes time for them to switch off and on. So it's not as simple as just saying, this unit is on and now it is off from one 5-minute interval to the next. You can have ramp rates for how quickly generators can actually go up and down. And there's also technologies that are a little bit more complex to model than the ones that I've described in this presentation. Technologies like batteries, pumped hydro, and other generators that depend on hydro inflows as well. The thing that I find that part of the reason I use Python for all of this is because what I end up doing when I build these mathematical optimizations is the majority of my code ends up being pandas for structuring all of these huge input data sets in the correct way to then build the mathematical optimization and then extracting them and doing the analysis of what comes out of them. Thank you.
Thanks, Jack. That was great. I'm sure there'll be plenty of questions. Has anyone got one they'd like to? The back there?
Hi. So you clearly have a sequence of models for different parts of your system. How do you get your pipeline of models to, like, how do you go from one model to the next in your sequence?
So that's a really good question, and you're right. Like, one of the very common workflows for electricity market models is we often end up describing 3 broad families of model, ST, MT, and LT. The LT model is the long-term or capacity expansion model, which is where you look at a 20-year horizon and you try to focus on what power stations should be built or retired optimally over this horizon. These models are huge. They can run for days, they can have tens of millions of decision variables and require a terabyte of RAM. Usually you try to get as much detail in that's relevant, but you still have to simplify to a certain extent because they're just so massive. The next one you have is a medium-term model, which is really around resource budgeting and allocation. So, for instance, you will use this optimization to decide if you have a large water reservoir, how should you really apportion that over the course of the year for the sake of modeling? And the reason you do that is because the final one, the ST, the short-term model, is one that you optimize over a couple of weeks. And if you don't give it a water budget, then the cheapest thing to do on its horizon is just to just dump all the water into the system and use it up.
Hi. I have one really, really short question and then a deeper question. First of all, what library was it that we saw on the screen just before?
So the library I was using was called GarobiPy, which is a solver library. There's also libraries like PyOmo that are put out by the National Renewable Energy Laboratory in the States as well. That's also quite good.
Gotcha. And then the other thing, so in terms of constraints, do constraints have to be constant values, or can they be variable or functional? For example, if we're constrained by the supply of energy, but we're building solar panels every month, then that supply is increasing. Can that be accounted for in the linear optimization?
Absolutely. So, and you're right. Like, some constraints are very simple, that it's just a single fixed level for the whole horizon of the model. Some constraints will vary over time, where you assume that. So, for example, one of the constraints we put in our model is we constrain how much it is physically possible to build in the grid in a given year. Because it might be the cheapest thing to do is we just, take every single Python developer and we go out and build, wind farms and batteries together. And whether, that's actually possible, we have to use constraints to represent reality in it. And then the other category of constraint, I guess, is the one here where you actually you can see here where it's a decision variable that's actually in the constraint, where you're allowing the model to set the optimal level of a constraint itself, provided there is some kind of cost or reason for the model to use it. If, for example, there was no cost to building a power station, then the model would do, funky things. Incidentally, the reason I've chosen different power stations is just so I could build up in the simplicity of describing them, not because I have a particular view of any particular power station in the grid. They're just really easy to describe what they do.
Thank you, Jack.
Sorry?
Hi, Jack. Thanks for another great talk. The model you showed us outputs which power stations should generate how much electricity to be optimal. But that's not, is that how the actual system tells them? I thought it just sets the price and you hope they do the optimal thing.
That's actually a really good question. That is one of the fun things that falls out of mathematical optimizations, in addition to all of the decision variables. You can actually, Dan, you're making me wish I'd made an extra couple of slides now. One of the beautiful things about the mathematics of these types of optimizations is you can, aside from it telling you exactly what every single granular decision should be, you can interrogate the constraints of the model. So you can actually go in after you've solved a model and say, okay, I saw that I had a constraint here for how much I could dispatch this power station for. How much slack is there left in this constraint? Or if you have a binding constraint that is limiting something, you can actually ask, what is the marginal value of that constraint? What is the cost? What is the value of alleviating that constraint by a single unit? And so, in the case of prices, I think how I mentioned that every state gets its own separate electricity price. The price that is set is the marginal value of the demand constraint for each of the regions in the NEM. This is, incidentally, the way that you would set a carbon price is the marginal price of a carbon constraint in one of these models.
And just sort of a follow-up question to that is like, do the generators, do they provide good data? Like, is there a set format? Like, is it standardized or is it really messy when it comes in?
So one of the beautiful things that the market operator has done is, because everything runs through a mathematical optimization, all the data has to be standardized, all the outputs come out of models, so it all goes into a SQL database, and it is all publicly available. So this is the reason, man, I'm so into energy. Because, okay, I worked for a few years as a data scientist. Most sectors, the problem was, how do I get any data, and how do I fix crappy data and combine it together? I bumped into energy, and it was the first sector where I was blown away, because the problem wasn't, how do I get data? It's all there, it's all publicly available. How do I fix it? Don't have to, it's all structured. It was, how do I understand it? And how do I wrangle immense data sets? The 5-minute data that I showed you, that's coming out constantly. Even the bids that the generators are submitting privately in real time are publicly released the day after. So as you can imagine, there are immense amounts of data on everything going on in the sector being released all the time. The really fun data set that I don't know any other country that does this is AMO has a data set that gets called causa pays. And it's basically, if you don't do what you're told, or if you do something wrong, it's how they assess how much you have to pay to make up for it. For instance, I promised I was going to run my battery at this time. I got dispatched, but I didn't do anything, so somebody else had to step in. And so the causa pays data set is tracked on a 4-second basis. And I had to do a project once where I had to look at every 4 seconds for the last 10 years for every power station and everything going on. It's billions of rows of data, all in fun 5-minute snapshot files zipped up, put in a zip file for each month. So there's a bit of wrangling involved. Incidentally, that 4-second data, interval data, is fascinating to look at. It's pretty amazing that kind of resolution. The big grid-scale batteries are so fast, they complain that that's not fast enough to pick up on how fast they respond to stuff.
Thanks, Jack.
Okay.
Hey, Jack. Great talk, by the way. Just maybe a little bit of an interesting question that I had in my mind for a few days is, with the rise of batteries in the NEM and the rise of auto bidders and using AIs in order to bid into the system, into the NEM, do you think it's possible for a certain Gen Taylor to actually collude in the market by having like different batteries in each and every region, and then, I don't know, simulating how the NEM is going to work using something of your work, and then saying, if I submitted X amount of bids here, X amount of bids there, I can actually control the market? Is that possible?
Possibly. I'm careful about commenting what can happen, but the battery auto bidding software is very interesting to look at, because at least the last time I dug into it, it's really trigger happy with rebidding, which makes it really annoying, because it might be that for one 5-minute dispatch interval, the auto bidding software for a unit might have bid and rebid 300 times in changing its mind constantly. So that makes digging into the raw data, normally I just try to stick with what the bids ended up being, but if you ever have to dig into that, sometimes the auto bidding stuff is just constantly just rebidding again and again and again, because whatever the most recent bid is ahead of the actual 5-minute dispatch occurring is what will end up occurring too.
I think one quick one. It's got to be quick though.
Sorry, just, kind of dumb, but just want to clarify what the pricing unit was. Like, was that in joules or in?
Oh, dollars per megawatt hour. I kind of.
Hour. Okay, yep. And then pro rata.
I made yeah, the unit's kind of vague.
For 5 minutes. So,
Yep.
yeah, right.
So it's like, so if,
500, then it's 100 for the 5 minutes. No.
yeah, if you dispatch 100,
Ignore.
No, I have the number. It's you divide it by 12. If whatever you dispatch for 5 minutes, you divide it by 12 because it's seared into my head.
It's $120.
Yeah.
All right. Well, thanks again, Jack.
Thank you.
Here is your stylish and functional.
Thank you so much.